The following video will demonstrate how to calculate some simple cut and fill volumes in n4ce. Our starting project is exercise 7 volumes, which can be located in the intermediate folder off of the n4ce training folder. We start with 2 models. One is an original ground model, or OGL. The other is a simple layout of 2 football pitches with basic batters calculated in another package. Our task is to improve on the design, as it currently does not balance. By this we mean that the volume of material excavated or cut is not equal at all to the volume of fill that must go back in. We will begin just by viewing the OGL model first. It is already backclothed with the playing fields, as you can see. Changing the color of the backclothed design to magenta helps it stand out a little more clearly. We don't need to see it for the moment though, so we will return it to its original color and remove it from the backcloth. Looking at it in 3D, we can see that not all of the data is in fact 3D. So, let's start by moving all the points to that surface to tidy it up. To do this, we first start by selecting in the spreadsheet view all the null level points. Having selected them, we will now add them to the list. This is a way of tagging them for future use. The yellow markers represent the listed points. We also need to enable the display of the markers so that we can edit them. To move the listed points to the current surface, we first need to set the pick mode to list. Now, using points, move, heights to DTM, we confirm the points in the list are to be operated on, then select the model to use as a reference. If any points lie outside the bounds of the DTM, then this will be reported. Any point still with a null level can be deleted. Refreshing the 3D view shows most of the data now sits nicely on the ground model. Now we can switch to the playing fields model to start to process the data. There are 2 playing fields with what look to be basic batter strings going around them. First thing we will do is model the points, in other words, generate a DTM, so that we have a surface we can begin to use for volume calculations. As this is pre-prepared training data, there are some groups in the model waiting to be used. Groups are essentially a way to assign a colorful pattern or shading to nominated triangles, so that during calculations, the results can be organized into the relevant groupings. Here we have 2 groups, one called Pitch A and the other Pitch B. The fill styles are totally user-definable, but it's suggested users stick to the shaded or solid modes. These are able to be exported to AutoCAD, but others such as crosshatch or checkered are not. Now we have familiarized ourselves with the groups, we can assign them to the relevant parts of the model. With Pitch A selected and using the Add group, inside Feature option, we just need to click the bounding batter for each field to assign it to a different group. Via the DTM, Edit, Delete Ungroup tool, we can remove any unwanted triangles. Volumes by prisms is the standard way to calculate the quantities between 2 surfaces. The option Projected Surface is selected by default, as this allows us to set the reference surface to another DTM. We are not interested in a table of results just yet. The text report will tell us all we need to know. But we do need to tick Swap Cut and Fill. This is so that the sense of the quantities, i.e. the cut and fill, is round the correct way. The basic rule is that if you are on the design model and are referencing an original ground model, then you tick Swap Cut and Fill. If you don't, then cut will be in the fill column and vice versa. Having set these options and pressed OK, we now select the reference surface. As there is only one to choose from, we can just press OK again. The volume report then appears, where we can see the volume for each group itemized. Pitch A is currently going to require a cut of over 6,980 meters cubed and a fill of 379, meaning there is a positive balance of over 6,600 meters cubed. A positive balance means there is material left over. Pitch B, however, is much closer to balancing. It is cutting 2,286 and filling 2,730. So it requires more material to be added to it than is being excavated. Hence the negative value of 444 for the balance volume. The totals beneath then combine these figures. So as it stands, the surface design would currently generate a surplus of 6,157 cubic meters of material to make this design work. Therefore, our task is to rework the levels of the pitches and hence recalculate the batters so that the pitches can be constructed to achieve a net overall balance of 0, or as close as we can get it. Step 1 is to delete the existing DTM and then inquire the distance between 2 points on opposite ends of the current batter. From the report window, we can see the existing batter is set at 1 in 4. To see if the current batter is even correct, we will use the batter tool under the Design tab to create our own. Having selected batter, all, we then click the line we want to batter and then indicate the side of the line the batter should be created. The pick mode was left in list mode, so it needs to be changed back to element. Using the batter dialog, we can configure the tool for our particular task. As we will probably be both cutting and filling, we need to enable the up and down option, plus set both the up and down slopes to 4. Next, we must define when the batter will stop, otherwise it will go on forever. In this case, we want it to stop once it hits the OGL model. So we enable that mode and set the reference surface to original. For now, we will keep the same code for both the cut and fill sections, as it will make editing a little easier. Also, to make the batter more realistic, we will fan the corners rather than have them so angular. Having pressed OK, we can largely see that the original batter is accurate. It's really in the corners, due to the fanning, that we see the main difference. However, the main issue with this design is that it's based of points that are easily 20 meters apart. Therefore, we are only sampling the original model at 20 meters as well. There could be large holes or ditches in the OGL, which would not be picked up having points at such a large spacing. We therefore need to densify the pitch string lines first. Then, we will be able to sample the OGL with much greater accuracy. From the Lines tab, select the Densify, All option. For this case, we will set the mode to maximum distance and the distance setting to 2.5 meters. This tells n4ce to only insert new points where there is sufficient room to do so, and no 2 points will be closer than 2.5 meters. The height mode can be left on linear interpolate, so just press OK to continue. Then selected new points will then be added to the pitch strings where there is space. With so many points, we may as well turn the level text off, as it's not really required. Now, the batter command can be repeated via the Alt+M shortcut to see what difference the additional points make. It's quite clear to see that had that design been approved, the initial quantities would not have been correct. The original batter string did not appropriately model the interface of the 1 in 4 batter to the original model. It's very important when battering to ensure there are enough points used to sufficiently pick up detail. Otherwise, the calculated volumes will be very different to those actually experienced on site. Now that we know this, we can delete the old batters, reform the DTM, and regroup the design before running a new volume calculation. The volumes are now much more accurate, but obviously do not balance. Pitch A still generates a large excess of material that cannot all be used up in the building of Pitch B, even though it required more material than it excavated. We therefore need to raise Pitch A and lower Pitch B. The degree by which we need to do this is what we now need to determine. The normal manual approach is to now, through a process of trial and error, raise and lower the design strings, re-better, and recalculate the volumes to see what works. From prior experience, though, Pitch A needs to be raised by about 1 meter, so we only need to do this operation once. Using the lines heights raise option, we add 1 meter to the Pitch A string, then re-batter and recreate the DTM. We will come to Pitch B when we have Pitch A balancing, so we will delete all the other triangles which are not part of Pitch A for the time being. Rerunning the volume calculation shows that by raising Pitch A by 1 meter, the quantities are very close to balancing. We could try and adjust the levels again, but over that large area, we could well find that the amount we need to raise the pitch could be 1 centimeter or so. Also, these figures are entirely dependent on the accuracy of the OGL surface, so there comes a point where raising and lowering the levels to get a balance approaching 0 may not be worth it, as the source data may not be accurate enough to allow the batter to be calculated to that degree of accuracy. That said, we now have a design for Pitch A that will balance much closer than the original scheme. Now it is the turn of Pitch B. Battering it with the same parameters as Pitch A shows the batter overlapping with the new design, but not correctly interfacing with it as it's battering to the OGL. We need to undo that and try something else. So that the batter tool can see the new batter of Pitch A, we first need to create a new ground model which merges the Pitch A design into the original ground model. To do that, we need to go back into the project manager and right-click the Models folder to access the new merge tool. This allows us to create a new model, which is the result of a foreground model cut into a nominated background one. Around the edge of the foreground model, n4ce will stitch the edges together to make a seamless surface again. Give the new model a suitable name and select the appropriate models. Then press OK. A quick check shows the new model is a combination of Pitch A merged into the OGL. This is the surface we need to use when designing Pitch B. Going back into our existing design model, we start the batter tool again. All the previous settings remain as they were, but remember to change the reference model to the new merged surface. There is still an overlap, but for now we will just delete the DTM, regroup it, and see how Pitch B balances now that it is interfacing with a slightly different surface. Because of the overlapping features, if we try and group Pitch B after grouping Pitch A, we see that it reallocates some of Pitch A's triangles, which we don't want to do. Undoing puts it back the way it was. So, to help make regrouping easier, and because of the overlap, we will lock the Pitch A group so that we don't accidentally reallocate triangles that we don't want to. Now, when Pitch B is grouped by inside feature, the overlapping section is not used. Having regrouped, we can run the volume calculation again to see what the quantities for Pitch B are like after battering to the merged model, and comparing it to the merged model as well. Pitch B still currently requires additional material to be imported as the balance is over negative 400 meters cubed. As a result, Pitch B needs to be lowered to a point where the cut and fill values are approximately the same. This process is essentially exactly the same as we did for Pitch A, but instead of raising the pitch, we need to lower it. Then rebatter and recalculate the quantities. However, in the designer version, we have an automated tool for balancing both feature string and DTMs. We will use the feature string option for now. Having selected it, like with the batter tool, we select the feature string followed by which side of the feature the batter needs to be created. The balancing dialog box also allows us to specify a bulking factor if needs be, where the material going back in cannot be compacted to the same volume as it was dug out, plus also a surplus where a quantity can be set that requires more material, which can come from elsewhere. So if a temporary stockpile on site contained 500 meters cubed, that could be added into the balance tool to make use of the additional material on site. All we need to do for our purposes, though, is to set the code, the slopes, and the fan angle to use. Then just press OK. The precise level for the pitch will then be calculated together with the appropriate batters. As we can see from the 3D view, there is still a small degree of batter overlap. But as they are the same slope, we can pretty much ignore the overlapped section. So we will break the overlapping feature either side of the crossing, delete the leftover feature, and then reform the DTM. For one final time, we will regroup the pitches and prove the balance tool has done its job by verifying the balance quantity for the second pitch. Grouping by one side of a feature helps to quickly group up the pitch B. Having deleted all the unwanted triangles, we can see in the 3D view how it looks. Everything looks fine, so we can proceed with the volume calculation. Remembering this time to project to the OGL, not our temporary merged model. Pitch B is still requiring a bit of material. Assuming pitch A does have 35 meters cubed left over, then we still require 56 meters cubed to construct pitch B to its current level. To demonstrate how little pitch B needs to change, we will drop it by 5 millimeters. That will mean the batter is not exactly 1 in 4 anymore, but given the accuracy of the original model and the degree of accuracy to which earthworks can be built, the overall change to the design is going to be insignificant. To demonstrate this, we will drop the level of the second pitch by 5 millimeters and see how that affects the volumes. Having lowered pitch B by that small number, we can see the amount of material required has dropped from 56 to about 25 meters cubed. If we drop it by a further 5 millimeters, we should be close to a net zero balance. It's not exactly balancing, but less than 5 meters cubed is acceptable for the purposes of this video. We can assume that the design is now effectively balanced and move on. Now that we have an effective design, we will plot a table of results. To do this, we just rerun the volume calculation, but this time enable the plot table option. The Prism Volumes dialog box allows us to control what detail is plotted in the table. Your initial settings may differ from these. Note a group key can be added to the table, which is configured via the group key button. If the hatch is set to a hatch style, then the density of the hatch is controlled via the scale setting. Smaller values result in denser pattern fills. By adding the units of the volumes to the column headers, we can see from the preview that the columns are not wide enough now. To fix this, we can click on the Columns button, which will allow us to override the default. There are no appreciable null areas, i.e., areas where the design is the same as the OGL, so we can turn them off, then set the column widths to suit. If this is a specification you want to use again, then before pressing OK, press Save. Otherwise, press OK to place the table on the model. It is also possible to label the groups with a leader arrow. To do this, we first need to create a new text style that has the size of the text set large enough to read whilst zoomed out. By going into the text style settings, we can press Add to duplicate the selected default style and name it appropriately for its purpose. Then, set the size large to make it easy to read. Now that the new style has been added to the project, we can select it as the style to use for the Group Label tool. If necessary, we can then play with the information that is displayed before it's exported to Cadd for finishing off or printing to PDF. It also helps to visualize the degree of cut and fill designs require. To do that, we need to generate an Isopachyte. This is a surface where each point in it represents the height difference at that location. To get the exact result, the routine projects all points from both models, as well as where any triangles intersect in plan. This results in a very messy-looking model, but all we are really interested in for now is the shading. Right-click the Models folder in the project tree and select New, Isopachyte. Give the new height difference model a name, and set the model to the design and the projection to the OGL. This way around where the model is above the OGL, the points will have a positive sense, and where it's below, the points will be negative. View the new model, and then using Alt plus F9, turn everything off apart from the shading. The default shading goes from blue to green to red, so negative values, cut, will be a shade of blue. As the levels approach 0, they turn to green. Then, in the positive zones, fill, they shift towards red. To make this simpler to understand, we will use custom shading settings to help make it more obvious how the cut and fill works. Rather than have a color change for each meter of height change, we will set it to 0.25. Then click on User Scheme and click the Intervals button to start to customize the shading. In this box, it is possible to set any number of height bands and assign colors to them. We could do this manually, but it is generally okay and much faster to let n4ce calculate the changes of color for us, once given some boundary conditions. Press Add and enter min, 0, and max. n4ce understands min and max and sets them accordingly for the current model. Now set the colors for those bands. We will use red for the minimum, white for 0, and green for the maximum, so we should see shades of red for the cut and shades of green for fill. So that this scheme can be used again, without having to manually set it up again, we can save it. Note that if a scheme already exists with the same name, you will be prompted to overwrite it. Should we ever want to use it again, we just need to click Load and pick it. Pressing OK updates the shading scheme so we can see the results. Colors look good, so let's place a legend on the model to help annotate the different depths of cut and fill that we are seeing. Backclothing the shading with the design helps provide context. We just need an idea of what the colors mean. To do that, we will use the Legend tool under the Tools tab. Set the interval to match the shading interval, and enable the Fill to Cut label. The rest of these settings should be fine, so press OK and place the legend on the model. Another reason for having the design backclothed is so that we don't place the legend over the volume table. The legend would perhaps be better if it were larger. First, though, we will remove the backcloth, as we now know where to put the legend. We also need to re-enable the Cadd backcloth, or the legend will not be visible after a redraw. Now, we set the scale of the model to at least double what it was. As the legend is generated relative to the current scale, by setting the scale higher, the legend will be larger too when we replot it. With the new larger legend in place, we can delete the one which is a bit small. Occasionally, users prefer to see a grid of levels over the shading rather than use a legend to identify the specific depths of cut and fill. That is easily accomplished by using the point grid option when right-clicking the model's folder in the project manager. Give the new model a suitable name and select the model to interpolate the levels over. Finally, set the grid spacing and the code to use, then press OK. Viewing the new model shows, as we would expect, a grid of levels whose heights are the depths of cut and fill at those particular locations. We have lost the sense, though, of how the cut and fill is distributed because the shading is no longer visible. We could backcloth the grid of levels with the height-shaded Isopachyte, but the text can be difficult to read in those situations because it blends with the colors in the lighter areas. Instead, we can apply the shading scheme to the height text itself. To do that, we need to edit the code table settings for the SL code and enable the height shading option under the Height Text tab. That makes it eligible to have its color changed to that of the height shading when the option for it is also enabled. That is achieved by opening the DTM Settings dialog box, loading the ISO shading scheme we previously saved, setting the interval to 0.25, and then ticking height shading. It's this height shading option that triggers any text annotation with the same option enabled in the code table to have its color set by the shading scheme. Switching back to the design model, if we turn off the group shading and then backcloth with the grid of height-shaded Isopachyte depths and the OGL model, we have the volumes and the cut and fill depths of the earthworks all on one drawing. To complete this exercise and further help illustrate our design, we will run some sections off. The first section we will run off is a simple long section that goes across the site. So, from the Sections tab, select the option Long. The default method for setting the cut line by sketching it and DTM facets in the profile box will suffice for now. Before we forget, we add the original model to the Models tab of the Long Section Properties box, so we also see it on the section. Then press OK. Now click the start and end locations of where the section needs to go. Then right-click, as we don't need to continue the section anywhere else. The section preview window will then appear. Initially, both models are being drawn in the same colors, so we will change the colors of both profiles to make the section easier to understand. Enabling the drop lines shows that when we come to plot it as a Cadd deliverable, we will need to change the default drop line settings or the section will be impossible to read. Closing the section view down invites us to give the section a name so that it can be saved and then plotted. If the section is not what we wanted, then pressing Cancel will discard it. Having taken a single long section, we will now take a series of cross-sections across the entire design. Again, we will sketch the center line the sections will be taken from. The offsets need to be set wide enough to cover the detail being sectioned. The interval controls how often a cross-section will be generated along the center line. Before pressing OK, we also need to include the original model in the section process. Indicate the start and end locations for the center line. Right-click, as we don't need to section anywhere else, and n4ce will take the sections automatically. As these are new sections, we need to quickly set the colors for the profiles. By clicking through the chainages, we can see the design interfacing with the OGL in each slice. If we click on Zoom to Extents, set the vertical exaggeration to 5:1 and turn off the drop lines, we can see more clearly what the section is showing us. Making the section preview smaller and moving it to one side allows us to see the live update in the model view as we cycle through each cross-section. Assuming we are happy with the results, we can give the sections a suitable name and close the preview down. To start to plot the section, we will go into the dedicated Cadd backcloth for this model. This shows us a Cadd view in the same coordinate system as the rest of the model. But the model data is in its background, so it can't be edited, just referenced. This is so that when we plot the sections, they will not be located miles away from the data and cause a zoom to extents to zoom so far out, everything becomes a dot. We will start by plotting the long section, so from the Sections tab, select Plot Single. Choose the long section and press OK. The preview shows us the section we are about to plot. Normally it's a good idea to lower the datum level and increase the top of box level to give some space around the section top and bottom. To reduce the number of drop lines, we will set their frequency to a regular interval of 5 meters. The section is now easier to read, but we are missing annotation where the section crosses the feature strings. To see that annotation, we need to go back into the default settings and add the code item to the list of items being plotted. By double-clicking on the code item, we can configure how the code annotation is displayed. If the text is plotted on the section itself, it will be very clear to anyone looking at it exactly where the tops and bottoms of the batters are. Hence, we will enable Plot on Profile. Otherwise, the codes will be plotted in their own row below the section and will not be as easy to identify. As expected, the preview now shows the codes of the features cut by the section line on the section itself. Pressing OK to continue pops up a message just warning the user that as codes are also being plotted, the drop lines will not always be at regular intervals. Press Yes to accept this and continue. Enter in a layer name to draw the section on and then place it a reasonable distance away from the design and its volume table. Occasionally, clients like to shade the cut and fill on the sections, so we will demonstrate quickly how to do that. From the Hatch tab, select Cross-Hatch Indicate and then pick the 2 profiles in the section. Note the design is actually 2 lines, so we do the other part separately. Select an appropriate hatch pattern and a suitable scale to control the density of the hatch. Next, we'll prompt for an origin and direction to start the hatch from. This is so that if the hatch needs to blend into another at a later date, then as long as the same origin and direction are used, then the hatches will join seamlessly. Repeat this process for the design of the second pitch. We just need to explode both hatches and delete these unwanted lines. It might look good to have different colors for the hatch when it is in cut to differentiate it from the fill. We could have set the color of the hatch before exploding it, but now we have exploded it. If we want to change the color of the lines, we need to do it in rectangle mode. With the long section plotted, we can now move on to plotting the cross sections. Clicking All selects every section for plotting. No empty sections is already selected. This is in case some of the first or last section locations are outside the scope of the design and contain no data. Initially, the preview has all the sections in a single column. Depending on client requirements, this can be changed to span the sections over a number of rows instead. Each section is plotting the coordinates of the section across the top of the section. For this example, we will turn that off. Notice also that the codes are being plotted on the section. This is because we added them to the previous long section, and that setting has been remembered. When plotting cross-sections, it's usually desirable to tick the height-based option for setting the datums. This allows each section to be as compact as possible, as the datum for each section can vary, depending on the data in it. The minimum height above and below fields ensure a certain amount of space is still preserved above and below the section. As before, we are notified that because codes are also being plotted, the spacing of the drop lines will not always match the interval set for the drop lines. Finally, we just need to plot the locations where the sections were taken. Otherwise, we can't relate them to the design. Picking cut lines from the Sections menu allows us to nominate which sections to use. Holding Control down allows us to select both section databases. Having set the colors of the line and labels, as well as configured the settings to your requirements, press OK. That concluded this worked example.